Hello, this is Meteorology 113, Lecture 7, Air Pollution Meteorology. This is the first lecture of Course Module 3, Outdoor Air Pollution, Ozone and PM2.5. This course module will comprise 3 lectures. The 2 following this one will be on ground level ozone and PM2.5. 1 lecture for each pollutant. These 2 pollutants are those of most concern today in terms of ambient air quality. This lecture will be on air pollution meteorology, covering various meteorological factors that affect how high air pollution concentrations can be once emitted from a source. This will provide some background that will help understand ozone and PM2.5 pollution. The outline of this lecture is as follows. We will first cover basic processes that occur in the air that affect air pollution, and the meteorological variables that these processes depend on. We will then focus on 2 specific meteorological aspects. The first is winds and pressure systems. The second is temperature inversions, a topic covered earlier in connection with the stratosphere. This time, we will focus on temperature inversions that occur close to ground level and therefore affect air pollution concentrations. Air pollution meteorology, processes and variables. We begin by reviewing a slide from a previous lecture, where the concepts of emissions from sources and concentrations at downwind receptors was introduced. Once an air pollutant is emitted, the concentration that results downwind is determined by various processes. The most obvious is the movement within the wind, the particular direction of transport depending on wind direction. This is the most clear example of meteorological effects on air pollution. Several other processes, however, can be seen on this graphic, all of which depended in some way on meteorological conditions. Dilution and mixing within the cleaner surrounding air as pollution travels downwind occurs due to gustiness and turbulence within the air. The rate of dilution is dependent on wind speed and temperature, more specifically whether a temperature inversion is present, which limits dilution. Chemical reactions can occur that react emitted pollutants to other species. The rates of chemical reactions are dependent on meteorological factors such as temperature, humidity, and cloud coverage. Pollutants can also be cleansed from the air by absorption in precipitation. Finally, some pollutants with long atmospheric lifetimes that don't chemically react or are absorbed in cloud or rainwater readily can remain in the air long term and be transported by winds over great distances. The next 3 slides will cover each of these processes, providing more details. First, wind transport, which is the air movement. This transports air pollution downwind away from emission sources. The meteorological variables at play are the wind speed, the wind direction, and the atmospheric pressure, which drives wind motions. Dilution and mixing is caused by turbulence and gustiness in the air. Dilution mixes polluted air with adjacent cleaner, unpolluted air. As a result, pollution spreads out and covers greater area as mixing increases. However, peak air concentrations at the center of pollution plumes are reduced because pollution gets mixed with cleaner air away from the plume center. The meteorological variables at play with dilution are wind speed, temperatures, whether it's day or night, for example, temperature inversions, and high and low pressure systems, which again drive the wind and may enhance or promote more gustiness in the wind that can dilute pollution. The next two processes are those involving chemical reactions. We split this into chemical reactions that occur in the gas phase and those that occur in the aqueous phase in liquid water. For gas phase chemical reactions, these are reactions of emitted species with others in the air in the gaseous phase. They reduce the concentration of the emitted species. However, new pollutant species can form as products of these chemical reactions. These are called secondary air pollutants. Ground level ozone is an example of a secondary air pollutant, which we will cover in the next lecture. Examples of air pollutants, as we said, are ground level ozone, various photochemical smog species, and not listed on the slides, some part of PM2.5, which is secondary. The meteorological variables at play are temperature and sunlight. For chemical reactions in the aqueous phase, this means reactions involving air species in the presence of liquid water in air, in haze, fog, or clouds. In this case, gaseous air pollutants dissolve and dissociate into ionic compounds in liquid water. These can form new pollutant species as products of these chemical reactions, again, secondary air pollutants. Examples of air pollutants formed in this way are the nitrate and sulfate components of PM2.5, which we will cover in a later lecture, acid fog, and acid rain. Meteorological variables that enhance aqueous phase chemical reactions are higher humidity, cloud coverage, and precipitation. On this slide, we cover two processes, atmospheric removal and long-range transport. Atmospheric removal refers to the removal of air pollutants from the air due to absorption into precipitation and the subsequent fallout of that precipitation to the ground. The affected pollutants are any particulate which can be scavenged from the air from rainwater, PM2.5, PM10, etc., and gases that are subject to aqueous phase chemistry such as SO2 and nitrogen dioxide. Precipitation is required for atmospheric removal in these manners. Finally, long-range transport is the movement of pollution long distances, hundreds of kilometers or more with wind. Two types of pollutants are mainly subject to long-range transport. The first are relatively inert species, those that do not chemically react readily in the air. The second are species that are emitted through large depths of the troposphere, major events, such as wildfires or volcanic eruptions, in which the polluted air from these emissions can be transported high up in the atmosphere and get caught up in very fast winds that exist in the upper atmosphere, upper troposphere. Meteorological variables at play are the wind speed and the wind direction throughout the entire depth of the troposphere to determine the direction that these major events can transport pollutant over. Air pollution meteorology. Focus topic 1, winds and pressure systems. Winds primarily affect air pollution by determining the direction that pollution blows the wind. This is determined by the wind direction. Seen here are three images depicting this. The left is pollution from a smokestack, in which the pollution plume travels with the wind from right to left across the image of the photograph from the stack. The middle image is of an industrial accident, where again the smoke from the fire blows in the wind right to left across the graphic. The right image is of a wildfire, in which plume travel is from left to right with the wind. While simple conceptually, a major challenge in these situations, especially for the situation of industrial accidents or fires, is to anticipate changes in winds that may occur during these types of events, since wind direction can change with time and therefore affect populations downwind of the event located at different locations from the incident at different times. To To assess longer period exposure, for example over a year, the changes in winds hour by hour over the year need to be simply summarized in some way for further analysis. The most common way this is done is through a windrose, an example of which shown on the right side of the graphic. A windrose is a graphical depiction of the hour-by-hour winds measured at a location over a long period of time, for example, a year. It depicts, using flags organized concentrically around a circle, the frequency of winds of certain speeds from certain directions. The directions around the circle indicate the wind direction. The radial distance from the center of the circle indicates the frequency of winds from that direction. Hatches along the flag indicate different wind speeds for winds along a certain direction. The best way to explain this is through example. On the right is an example of a windrose of hourly winds from a certain location over some period of time. Around the circle are the different directions that the wind can come from north at top, spanning from northeast to east to southeast to south, southwest, west, northwest, and north. These refer to the directions from which the wind is blowing. The longer the flag, the more hours over the year, or whatever time period is considered, the winds blow in that direction. With this example, the highest frequency of winds occur for southwest winds, from the winds that blow from the southwest to the northeast. The flag in this case radiates beyond the concentric circle, referring to 75 hours, meaning that for more than 75 hours, the wind is from the southwest. Contrarily, one can see that winds from the north, northeast, and northwest are much less frequent. Based on this, an air pollution meteorologist analyzing annual or longer-term pollution exposure in this location can assume that pollution transport will generally be due to winds from the southwest and other southerly sectors. This means pollution will generally blow from south to north. Also seen on this chart, the faster winds indicated by the orange and red hatches are generally associated with southwest and south winds. Winds from other directions, on the other hand, are associated with lower wind speeds. This slide shows another example of a windrose of hourly winds from a certain location over some period of time. With this example, the highest frequency of winds occur for north-northwest winds. The flag in this case radiates close to the outer concentric circle associated with 20% of the hours of the year. Contrarily, one can see that winds from the northeast and north sectors are much less frequent, as well as from the east and the northeast. There is also a secondary peak occurring for winds from the southeast and south through southwest sectors. Based on this, an air pollution meteorologist analyzing annual or longer-term pollution exposure in this location can assume that pollution transport will often occur with winds from the north-northwest traveling to the east-southeast. There will also be plume transport frequently to the north due to the winds from the south. Also, as seen on this chart, the faster winds are generally from the north-northwest. Winds from the south-southwest and south-southwest are associated with weaker winds. Winds are intimately tied to atmospheric pressure systems. Recalling from Lecture 1, atmospheric pressure is the weight of the atmosphere overlying a given area. The more weight, the higher the pressure. Shown on this image is a simple view of the relationship between air motion and pressure systems that typically occurs. Winds typically blow away from high pressure and towards low pressure. This is depicted by the arrows directed concentrically outward from the high pressure center and inwards to the low pressure center. Also seen is the typical vertical motion associated with each pressure system: sinking air with high pressure systems, rising air with low pressure systems. For low pressure, the air motion typically slowly rises upwards. In a sense, inward air motion into the low pressure system squeezes air upwards. For high pressure, air motion typically slowly sinks downwards. This slow sinking motion associated with high pressure systems is called subsidence. In a sense, the outward air motion away from the high pressure is replaced with air brought downwards. The subsidence associated with high pressure often gives rise to the creation of a temperature inversion layer capping the atmosphere near the surface. This subsidence inversion, as it is called, tends to trap air pollutants in the layer beneath it, since temperature inversions inhibit vertical motion of the air. We will show this in more detail later in the lecture. Key points summarizing what was just said are provided here. Pressure patterns strongly drive summertime flow over California, which, as we will discuss in the next lecture, is related to how ozone air pollution, common during summer months, is transported by the wind. Seen here is a depiction. During summer, a strong high-pressure system called the Pacific High is typically located offshore of California. Winds blow clockwise around and concentrically away from this system. Inland, strong summertime heating creates a shallow thermal low-pressure system. Inland, the resulting pressure gradient, or contrast over distance between strong high pressure offshore and lower pressure inland, creates strong onshore winds from the northwest direction blowing inland across California. These blow inland through topographic gaps of the Bay Area inland towards the California Central Valleys. In Southern California, a strong onshore wind occurs regularly across the Los Angeles basin during summer, moving polluted air further east and northeast, as we will see in the next lecture. The regular onshore summer winds bring cool marine air inland. Because of its regular occurrence, Mark Twain presumably said upon visiting the West Coast, "The coldest winter I ever spent was summer in San Francisco." A depiction of the effects of the summertime onshore wind across the San Francisco Bay Area is seen here. The green arrows are typical wind directions as occurring during summer, as onshore sea breeze travels inland through topographic gaps towards inland valleys. Air pollution emitted within the Bay Area from traffic and stationary sources get caught up in this wind. Some of it gets trapped in inland valleys, raising air pollution levels there, while other makes it further inland, affecting air quality in the Central Valley. Some key points summarizing this are provided here. Another key effect on air pollution related to pressure systems are stagnation episodes. These occur when high pressure systems become large and span a very broad area, staying fixed in place for days to weeks at a time. During this situation, winds can become very weak within the pressure center, which limits air pollution transport away from source areas and dispersion with cleaner air. High air pollution episodes can therefore result. Typically, stagnation episodes are most associated with wintertime and give rise to periods of very high particulate air pollution, for example, PM2.5. Seen here are two recent examples of wintertime stagnation episodes. On the left is an episode last winter in the eastern United States. The broad area of high pressure giving rise to this depicted here. Notice how broad the system, this high pressure system is and spatially expansive it is. This leads to weak winds and low pollution dispersion. On the right is an episode a couple years earlier during the winter in the western US. The broad area of high pressure giving rise to this depicted here. Again, notice how broad and expansive the high pressure system is. Air pollution meteorology, focus topic 2, temperature inversions. In Lecture 1, we introduced the topic of temperature inversions in connection to one specific example, the stratospheric temperature inversion. Recalling, a temperature inversion is a layer of air in which temperature increases upward, rather than the more usual behavior where temperature is lower, going upwards in the atmosphere. Within the stratosphere, temperature increases with height due to the absorption of sunlight by ozone gas. But temperature inversions can exist elsewhere for other reasons, and we will see examples in coming slides. A characteristic of temperature inversions is that vertical motion is strongly inhibited. Hence, the thunderstorm cloud in this image, and weather systems in general, do not grow further once it reaches the tropopause and encounters the stratospheric inversion. Weather systems therefore stay confined to the troposphere. For air pollution, we are concerned not with the stratospheric inversion, but instead inversion layers that form closer to the ground, within, say, the lowest hundreds to 1,000 meters from the surface. Visuals of this are seen on this slide. On the left is a typical image of Southern California air pollution. One sees dirtier air confined below the base of the temperature inversion, with cleaner air overriding this. On the right is the black and white image showing pollution and haze within a ground-based inversion, hugging the surface. The slides to follow will present two types of temperature inversions important for air pollution purposes: ground-based inversions and subsidence inversions. The first type of inversion we will present is the ground-based inversion. These typically form and become increasingly strong and persistent during multi-day periods during wintertime clear sky conditions. The stagnation episodes covered earlier, a couple slides back, are very conducive to the formation of these types of inversions. The graphic depicts a sketch of the situation. During night with clear skies, infrared radiation emitted by the Earth's surface escapes readily to space, not being trapped by clouds or water vapor. Little heat is therefore trapped within the lower atmosphere, and air temperatures near the ground cool rapidly. The near ground air thus becomes colder than the air above, and inversion layers at the ground can form. Persistent periods of clear skies, wintertime conditions lead to stronger and stronger ground-based inversions with each passing evening. The depth of this surface-based inversion is shallow, usually within the lowest hundreds meters or so above the surface. Wintertime pollution from auto traffic, residential fuel combustion, and other smoke sources can therefore build up to very high concentrations since the polluted air becomes trapped within this shallow inversion layer. Key points summarizing this are provided on the right. A special example of ground-based radiation inversions is shown on this slide. The situation when cooled air near the surface due to infrared cooling of the surface pools within valleys. These are called cold air pools and can exacerbate high air pollution episodes, since the polluted air then not only is trapped within the inversion, but also by the sides of the valley walls. Wintertime air pollution episodes within central California are another example where these cold air pools are a major factor adversely affecting wintertime air quality. Another example is shown on this slide, the pollution trapped near the surface in wintertime Salt Lake City, Utah. One sees the polluted air within the inversion and cleaner air above the inversion layer. Salt Lake City commonly experiences high particulate air pollution during wintertime associated with these inversion conditions. The second type of inversion we will present is the subsidence inversion. These typically form and become increasingly strong and persistent during summertime in California, as well as other similar geographic locations. The graphic depicts a sketch of the situation. On the left, we present again a graphic from an earlier slide of sinking air associated with high pressure. As mentioned when presenting this slide in detail earlier, the sinking motion is called subsidence and forms temperature inversions in a shallow layer of air overriding the lower atmosphere. The graphic on the right illustrates this. Notice that instead of the ground-based inversion, which is based at the surface, the subsidence inversion is based aloft, above the lower atmosphere. Typically, the base of the inversion, the subsidence inversion, or where the temperature first begins to rise with height going upwards, is about 500 to 1,000 meters above the surface. The mixing depth is a term for the layer of polluted air beneath the inversion within which pollution emitted from the surface is trapped. As mentioned, the most relevant example for purposes of this class is summertime in California. This slide illustrates this briefly. On the left is a visual of the Pacific high pressure system offshore of California presented earlier. The Pacific High is a persistent summertime weather feature of California. Subsidence associated with this high pressure system forms subsidence inversions. On the right is a photograph overlooking the Los Angeles basin on a summer day. Notice again how the pollution emitted at the surface is trapped within the mixing depth below the base of the inversion. For equal emissions, air pollution concentrations will be higher on days when the mixing depth is shallower and the subsidence inversion base is lower to the ground, since then there is a shallower depth of air to contain the pollutant. This is the case because the emissions become trapped in a shallower layer.